So my screen is visible, right?
Yeah,
Okay, so shall I start the session or do I need to wait for a few minutes?
yeah, we can start, I guess.
Okay, then. Let me get started with. Hello, everyone. So welcome to IIT and Gate classes. So in this session, we are going to see a special topic on gas dynamics that is part of your Gate syllabus. That is flow visualization. Here I have a very interesting photograph. This is actually taken from NASA. So can any of you recognize the technique used over here? So just to see like whether you guys are aware of flow visualization. So like you guys can guess actually. What you can do is like you can type in the chat box. I can see. Okay, fine. So I'm not going to give you an answer straight away over here. Let us try to get into the topic of interest. So at the end, I suppose you guys can recognize what technique we have here. You can see somebody's typing. Shadowgraphy. Okay. Okay, it's actually not shadowgraphy. It's actually a layering. Let us see each of these techniques in detail. Okay. So today's topic is flow visualization techniques, as I said earlier. And myself, Akshay, I'm from Indian Institute of Science, Bangalore. So visualization techniques. There are multiple visualization techniques, both in high speed as well as in low speed aerodynamics. As part of your BTech, I've done few of these flow visualization techniques. If you had opportunity to do some experiments in wind tunnels, did you guys do any flow visualization techniques during your lab courses in your undergrad? Most of you must have done it. Dynamics lab. Smoke, yeah, smoke visualization, right? You most of you have done the smoke visualization test, I guess. If you had a water channel kind of facility, you can also have some other form of visualization techniques, mainly a smoke visualization, right? Many of you are aware of. So like in low speed visualizations, so we have dye flow visualization, and we have seeding particles in the fluid, or we can have a smoke visualization. Let me just show the different photographs, which actually gives you different flow visualization techniques available in low speed. So the first one what you see in the right corner is the dye flow visualization. What we do here is like, so we inject a dye and to the fluid, and we see the pattern, how the dye takes or how the fluid actually takes over the body. That is dye flow visualization, usually effective in very low Reynolds number flows, right? So in moderate Reynolds number flows, we can have a seeding particles in the fluid like aluminum layers or something like that injected into uh, water. So it's these two techniques usually used in water channel where fluid viscosity is bit high compared to air, right? So we also have a very familiar technique, that is a smoke flow visualization. What we do is like we induce a smoke or a streak of smoke into the fluid, and we see the streamline patterns around the body of our interest, right? So these are all fairly well-known techniques in low speed, but in compressible limits, when Mach number goes beyond Mach point 3, so then the problem arises due to a change in uh, density or change in temperature of the fluid itself, right? So all these conventional techniques might not go well with the change in properties such as density and the uh, temperature of the flow field, because you see these seeding particles as well as the fluid should have a kind of similar properties, or else the compressibility effect will be different for different particles. So say like air is moving on a supersonic wind tunnel, and if you seed some aluminum flares onto that one, so physically the densities are very different, and the changes which happens across the shock wave will be very different. And also these are fairly high speed flows, and what happens, these particles act as a dust particle for the object you are keeping in a wind tunnel under test. So this dust can easily erode the object actually, right? So that is why considering these kind of flow visualization technique in compressible flows is a bit difficult. Okay, so I can see a question over here. Do we consider density or ignore it? So density is a part of your solution, right? But in incompressible limit, we fairly treat it as a density as a constant. It is not varying with respect to time or with respect to space, right? That is an incompressible limit. So there we are not ignoring it, we are treating it as constant. So density is not changing with respect to time or with respect to space. So it's a constant. So that is why it's a bit more easy to apply these kind of flow visualization techniques in a low speed. So if you guys can recall your basics of thermodynamics, right? So or basics of your fluid mechanics, the incompressible limit where energy equation actually uh, vanishes. Like we only treat continuity equation as well as the momentum equation as the governing equation. We never treat energy equation, or we never bring the energy equation into account unless and until the problem involves temperature change. So buoyancy driven flows or something like that. So which is out of scope for us as of now, right? So density is constant and temperature is an independent variable which really doesn't makes any of the differences in our overall flow fit. So it's fairly a constant. We usually treat isothermal idea. Do we consider the rate of change of density in compressible flow, or we approach differently? Okay, so the rate of change brings a very interesting question, because when you say a rate of change, is usually connected to two different terms, right? Like one is with respect to time and one is with respect to space. Like when you take a total derivative like d by dt of something, so you must have studied this total derivative. So which contributes towards two parts. So one is a local derivative plus a convective derivative, that is so velocity times grad dot the variable, whatever is you are interested in, or variable times, sorry, some const variable times del dot v, kind of thing. So it's a convective part plus the local part which comes into picture, and rate of change is a very involved topic as of now, so I am not going into the detail over here, but we will see how we can visualize the flows in compressible limits. Okay. Okay, so one beautiful reference I can give you is the Van Dyke's book, that is Album of Fluid Mechanics. So that is a very great book where you can see a different flow visualization mm, uh, figures. Okay, so why we need a flow visualization, right? So there are like so much of importance given to flow visualization, and why do we need in first place the flow visualization? The first and foremost reason is it gives a good qualitative measure of the flow picture, so it gives a overall picture of how fluid is flowing around a body. And the next one is like unsteady effects can be visualized with a well time resolved movies. So this statement might be too much of a technical one, but what I can say in a broader ways, you can actually get the effect of unsteadiness if you have a lengthy movie, so then you can visualize it by frame and see the flow how it is evolving. So that's the very rogue way to say what this statement means is fine. Okay, then there are certain scenarios where direct measurements of quantities like pressure or temperature or velocity, whatever, it becomes too difficult for certain scenarios. Like maybe the geometry is uh, the whatever you are studying is a bit more complicated, where you might not have access to put the sensors. So then this visualization gives a good picture of the flow picture. So in those scenarios you might have to rely on the flow visualization alone, where you cannot put a physical sensors, especially like in high speed flow, say like all your physical sensors like pitot tube or pitostatic tube, whatever you use in low speed uh, fluid mechanics context, in high speed it becomes relatively difficult, because which itself creates disturbance in the flow field, and which can physically change the problem itself. So that is why in those scenarios a flow visualization becomes the sole choice for an researcher or whoever is trying to study the physics, right? So that is one more reason. And there is a famous statement like we often say in the field, like one good image of the flow field is equivalent to 1,000 hours of the research work. So it's actually true, because if you can get a uh, very good flow field image, that gives you a much more information than the collective data you can get it quantitatively in a different way, right? So now we will move on to high speed flow visualization technique. So as of now I gave an introduction to what flow visualization is and why we need a flow visualization techniques, and mainly we focused on the low speed flow visualization technique that we are kind of aware. Now we will move on to a high speed flow visualization technique. One one of the topic you guys must have studied in your higher secondary schools or in high school is in your physics is optics, right? So there you might have studied how light travels in a denser medium, or how when the light is traveling from one medium to another medium, what happens to those light rays, or what happens to wavelengths of light, or those kind of stuffs, right? You guys have studied this concept, right? Refraction, right? So when you put it through a prism, what happens, and when you put it through a glass, what happens, when you put it through a water, what happens? So all these stuffs you guys have studied. Can anybody tell what exactly is a refraction is? Bending of light path from normal. Okay, that is a part of the answer. When light travels from one medium to another medium, it bends. Again, it's a half-cooked statement, but it's okay. Snail's law. It's actually not Snell's. Snail's law is yeah. It explains the or it actually correlate the bending to the density of the medium. That is fine. So I said like all those statements what you have given, it's a half cooked one. Why? Because yeah, light actually bends when it travels from one medium to another medium. I wanted the full answer. So like in which direction the light will bend? That completes the statement. So like there is a figure in front of you. You can actually see and answer it. Towards the normal is not exactly the answer. It bends towards the denser medium, right? If the light is traveling from lighter medium to a denser medium, the path will bend towards the denser medium, right? That is what you can see. Like there is a glass piece and you have a laser light which is coming from atmosphere and which is bending towards the medium, right? It bends towards higher density, right? Right. So that's the whole purpose of using these techniques, you see. So the refraction, the idea of refraction, and we have already studied the Snell's law basically comes out of this geometry, nothing else. So this is evident from this picture. You can see the light is traveling in this way and which is bending towards the medium, and when it passes from denser medium to lighter medium which moves away from the medium, that means it always bends towards the denser medium, and when it passes from denser medium to a lighter medium it bends away from the medium. So that's the whole purpose. So this is very important concept we have to keep in mind. What happens when light rays passes through a different mediums, right? This is very very important. So now why I am bringing this concept is, this is a classic physics or a textbook problem we all been went through during our high school days. So the idea of refraction, when the light travels from one medium to another medium, this is the whole this is why we actually see a rainbow in sky or something like that, like when it passes through a water droplet and all, right? So this is nice. So now what we can actually extract from this idea is, we know that when the flow is a compressible, that means like when flow reaches Mach number greater than zero point 0.3, then there is a change in density occurs within the fluid medium. So now if we can extract this feature of change in density and combine the optics what we have studied in our high school physics, we can get a very beautiful flow visualization techniques, right? That's the whole purpose of discussing this part, the optics. We can use this optical properties of change in density of the medium to an advantage to visualize in more detail. This is non-intrusive method, like we are not putting any seeding particles or whatever into the flow field. We are allowing flow to happen normally, whether it is a flow of gas or flow of air. It can happen easily, but there is a change in density within the medium, so that we can actually use to extract the features by passing a light through the medium. Okay. Yeah. So now we see what are the different techniques actually uh, we can come up with using this basic idea of optics, right? So I am slightly going back to our discussion on refractive index as a function of density that you guys have already studied. This is slightly more involved formula. This is the same idea. You can see this is called a Gladstone-Dale equation, which basically gives a refractive index as a function of medium density, where this rho s is a standard reference density. Okay, and beta is the constant. Okay, so this is the same that Snell's law tells you in terms of geometry, right? So that gives you in terms of sine of angle is equal to change in refractive index or something like that, or refractive index of the medium in terms of sine of an angle. So this one gives in terms of density. This is called equation, owing to this these two scientists who actually came up with this formalization of this relation, right? So here what you see is I can relate the refractive index to the density of the medium. So that's the important point we have to take. So from this idea we are actually bringing out the different flow visualization techniques that can be applied to compressible flow fields. Okay, so now let us see in more detail what happens when the light passes through the medium, right? I will give two scenarios. Say I have a medium like this. Okay, and I have a light wave coming like this, and say I have a density gradient which is varying in this direction. Okay, so it is perpendicular to the light. So the density is varying perpendicular to the light. Now again I have a light which is coming in, but I have a medium now. I have a medium now where my density gradient is parallel to the flow field. So light rays. So now can you tell me what happens when the light ray passes through this medium, say medium A, and what happens to the light rays when it passes through medium B? In one case, I have a density gradient which is perpendicular to the light direction. In other case, I have a density variation which is parallel to the density gradient. The light ray is parallel to the density gradient. The gradient in the sense how density is changing. In case A, what happens to the light rays, and case B, what happens to the light rays? Yes, yes. So that is correct. In the first case, the light rays will bend perpendicular, and in the second case, it will remain parallel, right? Because you see, as the light comes, the light ray comes, and when it sees a change in medium which has a density gradient which is varying in this fashion, that is perpendicular to the direction, then what happens? It tries to bend towards the higher density. So in this case, what is happening? Here I have different density, here I have different density, here different, here different. So in perpendicular to the light way, what I have is difference in density. In that case, what happens? The light ray will bend towards the higher density with respect to your original direction. It is making an angle theta. It can be locally different also. Okay, in the second case, what is happening? The light ray is coming and seeing a density which is different, but the density is varying such that here I have density, here I have different density, row 3, row 4, but this is varying only in this direction, not in this direction. So in this case, what happens? The direction of the light as well as the change in density, both are in the same direction. The gradient of density as well as the direction of the light, original path, both are in the same direction. So it actually bends towards that direction, but it is actually in the direction of the light path. So there is no need to bend, so it will just pass through, right? So you are able to understand this idea, right? Because it's important to know this idea to go further, right? Okay, so now let us try to understand this idea into more physical pictures. So say like I have a wind tunnel, this section of a wind tunnel. Okay, so now I am weaving from the top. Okay, so I am keeping a wedge. Use a different color for this. I have a wedge in top view. It looks like this, right? It's just a rectangle kind of thing. So now if I look at the same wedge in the side view, so how it looks? It looks like this. Yes.
So in the B scenario, I have a little doubt. There is a change in the density, right? Here
Ah.
also. So the the light will bend right. Yeah, how
Hmm.
it can be done? I didn't get it.
No, in the first case, see the density is actually varying in this fashion.
The B also the density is increasing, right?
Density is increasing or decreasing, that is not the case here. The density is changing in this direction. Say like density is increasing in this direction, not in this direction. Are you able to understand this part?
So in the both scenarios, it looks like same, right? I mean, here row one, row two, row three,
No,
they are
no, 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 no. No. Here you see, say this is a streamline. Okay. Each of these lines represent the streamline. Along the streamline, the density is constant, but across the streamlines the density is changing. That means the density is changing parallel to the light direction. Got it?
okay.
Yeah, so in this case, say each of these are again streamlines, but the density is changing along the streamline. Along the streamline, now density is not a constant. So now when the light sees this kind of scenario, it sees a change in density which is perpendicular to the direction. So now it tries to bend towards the higher density values. In this case also, it tries to bend towards the higher density values, but that higher density values are already aligned with the direction of the light. It is bending, but it is 0 degree. Got it? Because this is important to understand the physics we are trying to explain further. or understand the method we are trying to establish further. Now you see, I have a wedge. So I have a supersonic flow like this. Okay. So from the top view, from the side view. So this wedge can be like single angle, or you can have a symmetric wedge. It's fine. So now when it sees a supersonic flow, what happens in front of wedge? Guys, you guys must be aware of. So we see a formation of a shock wave, right, in front of wedge, right? So this part we studied. So if you like, I assume you guys must have went through a gas dynamics course in your BTech. So you have studied the what happens to the properties across the oblique shock. So whenever there is a shock wave, you see a property which is going to change across the shock wave, right? Upstream of this one you have a constant properties, downstream of this one you have a constant properties, but across the shock you see a change in properties, right? Not just density, all the properties will change: pressure, temperature, velocity, density, total pressure. Total temperature remains constant, being it's adiabatic, right? So the properties will change. The important property we are interested in now for the flow visualization technique is the density will change. In which direction? On the direction of the flow, right, across the shock wave, right? If I take a reference line over here, if I take a reference line over here, this line will pass through all the way from here to here, the top, in the top view if you see, right? So along this line you see the change in properties, but across the shock wave you see a change in property, not here or not here. Here the properties are constant, here the properties are constant. Only across the shock wave you see a change in properties, right? So now in which direction, if I pass the light like this, in which direction the light has to bend? Towards the top or towards the side? Yes. Which direction the light will bend now? Towards the side, right? Why there is a question mark? No need to put a question mark. So you should be confident. Okay. It should be towards the side, right? Because the density is changing in this direction, that is perpendicular to the light wave. But in this case it is parallel, so nothing is changing, only the medium is changing from atmospheric to test section, the gas. So there is a different gas. So other than that, like it's parallel. Nothing is changing in this direction, but everything is changing in this direction. So the light will bend in this direction. That's the whole purpose, because when you send a light rays, you are not going to send one single rays, you are going to send a bulk of light rays. So you should be able to understand how it behaves. Okay. Now we can understand how it is helpful, right? So see, now I have a test section, right? So now the the bulk of light rays will coming to the test section. Okay. Now there is a wedge which is sitting over here, so across which we see a change in density. So if I say this as my reference line. So all these rays which passes ahead of this, they just go straight because they don't see any change in properties perpendicular to them. But all these rays which passes post shock will also go straight. They don't see any change in properties perpendicular to the direction. So all these rays which passes through this shock wave now will see a change in direction to the, let me use a different color. They see a change in direction in the light beam. Right? Understood till this point? So now, if I put a screen or something like that to capture the intensity of the light which is coming on and falling, right? So now what you see, here you see a normal intensity. Here also you will see a normal intensity. Here also you will see a normal. Here you don't see an intensity. Here you see a higher intensity because already there is a light which is coming, and there is a light which is coming because of the bend in this light ray. So there is a high intensity light will fall in this place. So now if I map out in originally, I would have got intensity versus x as a constant line, right? If there is no wedge which is sitting over here, I would have seen the intensity as the constant function of x. Since now I have a wedge which is sitting over there, which is creating a shock wave, now I see a change in density. Now what I see is, I see an intensity like this, which is dropping and which is rising. You see now what's happening? So this region becomes darker, this region becomes brighter. Yes or no? Right? This is the very idea from which we can actually extract different flow visualization techniques. So let us now look at the graph very carefully. So what we got is like we can actually get an intensity versus location, something like this, right? So now you see, if I have a bulk of light rays, for which like if I have some kind of reference frame where the light is falling, you see no light falling over here, so that will bend like this. Okay, so now if you frame this, what are the things you can actually measure from this? If you have a scenario like this, what are the things you can actually measure? One thing you can measure is the displacement, right? How much this light is bent, the displacement x. The other thing you can measure is at what angle the light is bending, the theta, right? The one more thing we can measure is the difference in phase, actually, that I will explain a bit later. So the difference in phase is, so compared to your original direction of the light ray and the bent light rays, if they are falling at different instances, how much difference they have with respect to each other. So that's what the phase difference is all about. So that is much more involved because it also involves with the light which is passing at a faster rate to a slower rate. So that's where the phase difference comes, right? So the three things we can actually get is, the information is the displacement, second one is the angle of deflection, I can say. The third one is phase difference. Okay. Okay, somebody has a question. Could you please tell again how there is drop in intensity? Okay, this is very straightforward, right? Like you see, there is a change in density in this, like perpendicular to the direction of the light. So then what happens? The light bends in this way. So there is a lesser light which passes through this portion compared to the light which is passing in this portion. So now what happens? There is already a parallel beams which is coming over here, and there is some light which is actually coming because of the deviation. So both will come and hit at that point. So here you see a brighter region compared to here, because here in theory there is no light, in practice there will be a less light. So that is darker, this is brighter. Got it? Okay. So these are the three different things we can measure. One is displacement x, the angle of deflection of the light ray, that is theta, and the phase difference. This idea phase difference you guys must have done in your high school physics. You guys did this interferometry experiment, right? Or diffraction kind of experiments, right? You saw this diffraction patterns, right? Black and white strips of lights. Guys, you guys must have done this Young's experiment or something for the diffraction, right? To study the diffraction of light. Yeah. So that phase difference is coming out of that idea actually, the diffraction. There you have studied that, like whenever two light beams are in phase, you guys get a brighter band. Whenever two rays are in out of phase, you get a darker band. That is how you get the diffraction pattern. That's the whole purpose of that experiment you have done. Double slit experiment. Yes, Young's double slit experiment, if I recall it correctly. I am also recalling all these things along with you. Okay. So there you have studied that is the other thing you can actually measure, the phase difference. Why this is important, the displacement, angle of deflection, or phase difference, based on these three method or these three variables what you can actually measure, you can have different flow visualization techniques. Okay, so that is what I am classifying over here. So the first one is shadow graph, which gives you an idea of the displacement. The next one is Schlieren, which gives you an angular deflection, which is basically gives you a angular deflection. The other one is interferometer, that is going to give you a phase change. What it is actually sensitive to, the shadow graph is actually sensitive to the second derivative of the density, because what you are going to see is like you are going to see only the dip and rise, nothing else. So it is basically going to give you a second derivative of density. So whenever you have a curve like this is nothing but a second derivative, right? So the next one is sensitive to density gradient, that is Schlieren. And the last one, you can actually get the direct measure of density, which is sensitive to a density itself, and which is a measure of phase change, which is due to the idea of a phase change. And how these methods work in an actual laboratory frame. So like if I want to set up a shadow graph, which is relatively easier, and if I want to set up a Schlieren, that is moderate. So like it's not that easy, but it's not as tough as interferometer. So interferometer setup is much more difficult because you have to see all this involves optical setup. So you have to precisely put the lenses and mirrors, whatever which changes the light direction and all, very precisely. Because of this, this becomes difficult to set up these techniques, but it's a worth spending time to set up these techniques because it gives a much more information towards the flow field. Okay, so now let us see, if you see in a textbook kind of in a textbooks, you are going to see these kind of graphs. So you see, this is the second derivative. This looks like this. So that is what dark and bright band represents, right? So the first derivative always looks like this, and the density actually changing in this direction. You have a constant density to some extent, and there is a sudden change in density and again constant. So it is direct density change. It's the derivative of this curve, first derivative. It's the second derivative of this curve. Okay, so based on this idea, we can have either shadow graph, which is sensitive to second derivative, Schlieren, which is sensitive to first derivative, and interferometry, it is actually sensitive to density itself. Okay, so now I am going into individual techniques and their optical setup, how it looks like. We understood these three different techniques, right? So now there is an image in front of you, which is a bullet which is traveling in a medium, say. In front of that, you are able to see a bow shock which is forming. So can you see that in which direction the density is changing? Can you guys tell me, with respect to your reference frame, you are seeing the image, whether it is left to right or right to left? By seeing this figure, you should be able to see. Is it right to left from your reference frame, not from the image? Okay, the question is actually not complete, because if I just say in which direction density is changing, it both of that is correct. It is changing either right to left or left to right. So in both directions, the density is different. The thing here is like in which direction the bullet is traveling. That is a much more precise question to ask. It is traveling in this direction, right? That's what's important over here. Okay. So it is just an image which shows the shadow graph. So like it's taken using shadow graph technique. Here we can clearly see the bow shock. So now if I go on to explain how this shadow graph setup looks like, so it's relatively easy to set up, as I said earlier. So I have a light source which eliminates the light, and I can have a pinhole, sorry, lens. Use so I can have a lens. What does it do? It actually converges the light to a point. So ultimately, what we trying to achieve is the point source. Okay, so point source that will be much more helpful. So now at this point, what we do is like we use a small slit. So at the focal point of this lens, we will keep a slit. Okay, so from here again, the light will diverge. This is basic optics again. I'm not going to explain this. So now this point, the light will diverge. Now at the end of this, I will keep one more lens. That is the property of that lens is like whatever comes, that will make it parallel. So I am keeping the lens which makes whatever comes into here. So all the diverging beams will be now parallel after passing through the lens, right? So now I have a nicely collimated beams of light which is going towards the test section. So now I am having a test section. Usually all this test section will be provided with an optical window through which light can pass. Okay, which passes through the test section. And at the end, you provide a screen or usually high speed cameras which can record whatever is coming and hitting onto that. Let us have a screen. You capture the light which is coming after the test section. So see, I have a flow which is going in this direction. Say it is low density region and this is high density region. Okay, when the flow goes from low density to high density, the light will actually bend towards high density. And what you see on the screen is here you see a lighter region, here you see a darker region. Say if I have a wedge, this is a simple shadow graph technique, nothing else. So we are using just the light source and we are making it to parallel and we are recording it. Got it? So this is how the conventional shadow graph setup looks like. Okay. Now say like if I have a wedge which is placed over here, say in this same thing. So if I have a wedge which is placed, So we know like across the wedge we should be able to see a shock wave, right? Across the wedge we should be able to see a shock wave. So in shadow graph image, what you actually see is you see a dark region first, and then you see a brighter region after that. So that means the dark region is the place where you have a low density, and the bright region is the place where you have a high density. So across which the density has changed. So what you qualitatively infer is, so that is the location where the shock is present. The dark to bright, when it changes, that is the location you infer as the shock wave. Got it? So now if I see like I have an expansion corner after this. So here I should be able to see an expansion wave. So in this scenario, what you are going to see? So can anybody tell what you see here? Whether dark followed by bright or bright followed by dark in the expansion corner. If there is an expansion fan sitting over there, what you see? Dark then bright or bright then dark? Bright first then dark, right? Because in that case the density is, the higher density is in the other direction. First you have a high density, then you see a low density. Across the expansion fan the density decreases, because of which the light will bend in the other direction. So you see a darker region later. First you see a brighter region, then you see a darker region. That is how you infer it as the expansion fan. There is a flow expansion happening. That is how you infer. So got this idea, right? The shadow graph. Yes. So this is one more photograph of the aircraft which is under test. So here we can see the again the shadow graph image. So here you can clearly see, right? So there is a dark, immediately after that there is a bright line. Can you see that? Yeah. So by looking at the picture itself, you should be able to say like which technique you might have used, people might have used in these cases. Okay. So now moving on to a steering technique. So here I am keeping few videos from my own experiments. So I used steering technique. So here you can see that there is a conical shock which is sitting in front of the cone, and there is a bow shock sitting in front of the bluff body, and there is some shock structure which is moving because of combination of two bodies. Okay, so here you see much more details compared to what you saw in the shadow graph, right? So in the shadow graph you are able to see only the shock structure clearly, nothing more than that. But in this case, in the Schlieren video, you can see a few more structures like the small eddies, those things, right? Because it is sensitive to now density gradient. See, it is not a second derivative, it's a first derivative now. The important thing you can see here, it is sensitive to density gradient, because of which what happens if I have a symmetrics. So like in this case my density gradients are in this direction. So this is how my setup is, like in x direction I am setting up. So that is why you see the light region to bright region, what you see, it is in this direction. So here also I am setting this clear in x direction. The sensitivity is in x direction. So in this case, I am setting in the y direction, or in other way, this direction. That is how I can see there is a dark following the bright. So that is where the shock wave is. So there is also, you can see the bright following the dark. That is where we call the shear layer. So we are not going into the details of this flow now. So these are all set in x direction or in the y direction. Say for sake, like if I have a flow field like this, same thing, if I had set in this direction, sensitivity is varying in this direction, then what you see is, note here, what you see is, you see a bright following the dark here and the dark following the bright here. So you see in a different way in both the planes. If I had set my reference plane over here, so then what you see is, here to here you see a bright to dark, and here to here you see a dark to bright. So in this case, what happens, you cannot just infer whenever there is a dark region as shock and whenever there is a bright region it is something else. So it can differ depending on the direction in which you are setting. You're getting my point, right? In the shadow graph, you don't see that one. You just see dark and bright. But Schlieren is sensitive to density gradient, because of which it actually also depends on in which direction you are actually setting up. So how you decide the direction, that I am going to say, show with the optical setup. Uh, it is fine if you are not able to see the mouse pointer, it is fine, so that's not important. So I am going to show the optical setup. There you will get a much more clearer picture. So the main takeaway you have to take from here is, it is sensitive to density gradient, and depends on in which direction you are setting up that gradient. The sensitivity in which direction you are looking at, so that depends either in x direction or in y direction. Based on that, your shock and other related structure actually differs. You cannot always infer bright to dark, so bright to dark or the dark to mm, bright as shock waves. So like, you have to think based on your setting, whether really you are having the shock wave or the expansion corner, based on the direction. Got it? That's the main point you have to take. In this video, you can actually clearly see many things. So there is a shock wave as well as there is an expansion corner. So here you can see the expansion wave in the other color. So all these things you can actually see. Like, I think I am using the black color. That is why you guys are not able to see the mouse. So you see there is an expansion corner. So there is a shock wave. So this is coming as the bright and this is coming as dark. Okay, so that's not important. It's an hypersonic flow experiments around Mach 6 flow. But so our idea is to understand the method. Okay, so let us move on to the optical setup. So the steering is relatively difficult to set up compared to shadow graph. So what you have, all these upstream settings are same. Like, you have a light source, so from which you are making it a point source, and from which, like, you have a slit over here, and you have a light source from which the light is coming. Like, you have a lens which is actually converging to a pinhole, and light is coming in all direction. So this part is clear. Then you can have a lens. Then you will have a lens which makes this beam to a parallel, which makes this light parallel column tip. Okay, towards the test section. Then you have a test section. Then you have a test section. Light beam passes through that. Then instead of screen, what you do is you put one more lens actually. So what does this lens do is whatever the light which is coming to this lens, this will again converge to its focal point. So in the focal point, what you do is you keep a knife edge. Why we are keeping this knife edge, I am going to tell in a little later. We will keep a knife edge, and after that, again it will diverge, and here again you will keep a lens, or you will record it through camera. So camera is also having lens, so you are going to keep the camera over there to record it. Okay, so camera lens or whatever. So now here you see, instead of just screen, what you are using, you are actually using the lens, which again converges at the focal point of this length. You are going to keep a knife edge, and from there again there is a divergence in the light beam. There you are going to record it. So now what does this knife edge is going to do? That is important. So now see here, we know that the light will bend towards the higher density medium. This is high density, and this is low density, right? So light travels at different speeds at different medium now. Because of the high density, it travels at a different speed compared to the constant density medium. So now what happens, all these parallel beams which are coming on and hitting onto the lens will converge to its focal point. Say if the light waves which is coming at a different angle, what happens? They cannot converge to a focal point, right? Because it is not coming onto this lens in the same angle, right? So all this parallel beam will converge, but the beams which are coming and hitting at a different angle, they are not going to converge to this knife edge. You are getting my point? They actually skip the knife edge. You are getting my point? This is your basic physics, right? So like say I have an object, right, which is standing. So I have a lens, okay, which has a focal length f, and this is 2f. F plus f, this is 2f. So if the object is standing between f and 2f, so where does this image will fall? The image of this object, the image of an object will fall somewhere beyond this two, right? So it is not going to fall either in F or in 2F. It falls away from that, right? So this is what you have studied during your high school physics. If an if an object is sitting between the F and 2F, so that the image will fall beyond 2F, right? Or at 2F. So that's the case. So this is the same scenario now. For all these things, they are falling onto the mirror at a different angle. That is like an image which is coming at a different angle. So that is going our image which is sitting at between F and 2F. So all those things are skip this focal point and falls far away from that. So that is why what happens when you put a knife edge kind of thing, what it does is it blocks all this rays which is coming parallel in the test section, and which allows only those rays which are not parallel. So in that sense, it actually enhances the sensitivity. In practice, what people do is like they are not going to cut off everything which is coming. They are going to cut the part of this light. So they are not going to cut everything, the part of this light, and allow some amount of light, so that there is a dark region which is coming going there. So now it actually enhances the sensitivity. That means like the brighter region becomes much more brighter, and the darker region becomes much more darker. So that is how this knife edge will do. And depending on the direction in which you are keeping this knife edge, you can keep this knife edge cut either in this direction or in this direction, or you can cut in this direction or in this direction. So depending on the direction in which you are cutting, either horizontal cut or the vertical cut, so depending on that, you can have x gradient of sensitivity, so that is dou rho by dou x, or you can have y gradient of sensitivity, so that is dou rho by dou y. So you can either have dou rho by dou x or dou rho by dou y, depending on the direction in which you are cutting the light rays, in x direction or in y direction, horizontally or vertically. How can you have a light rays which are parallel and above the knife edge? Because knife edge is sitting exactly at the focal point. So the job of that lens is to focus all the light rays which is coming parallel to it towards the focal point, right? That's how the lens work. So you are keeping knife edge exactly at the focal point. That is how I am saying. That is why I am saying all these setups look simple in theory, but when you try to set up, it is much more complicated because you have to match all these focal point correctly. Setting this setup is not that easy task. It takes days and days to set up a very good Schlieren setup. Okay, so this is a very simple way to set up a Schlieren, and so this is what you see is the standard Schlieren setup called a JED. It is mostly or widely used Schlieren setup. Instead of lens, what they use is a concave mirrors, which will collimate the light beam. So instead of lens, you have a light source which um, like the light will fall onto this concave mirror, and which will then collimate the light towards the test section, and you will be having one more concave mirror which will again um, converge the light. So all this parallel beam will be converged to the knife edge, and knife edge depending on the cut, so you can vary the intensity and enhance the density gradient. Then it will actually go into focusing lens, and from there that will be directed towards your screen or the photographic plate. In many cases it will be a high speed camera. So I am going to show you the setup I have used during my work in the hypersonic wind tunnel. So I had a light source, I had a slit, and then it is falling onto a concave mirror. It is culminating towards this test section, which is received at the concave mirror 2. Then I had the knife edge at the focal point. Then it is going to fall onto the concave mirror, and I am just enhancing the spatial resolution with the convex lens that will fall onto my camera. So here you can see my test setup. Can you see the lens? This is the knife edge. You see, this is the knife edge. Actually, it's very hard to see. So can you see this stand over here? This is my knife edge. So I'm using the razor blades as the knife edge, and then I have the mirrors, camera, high speed camera, which is recording. This is my test section through which the flow is coming. Here you see a tiny part, that is the other mirror which is standing there, and we had a light source which is sitting over here. So from here we are shooting the light which is coming like this, hitting like this, going to the knife edge, then into the this um, mirror, and then to this lens to camera. You guys are able to understand this Z type setup. So you trace, it is just the Z, right? So shall we move forward? It's almost time, so I have to give one more thing, that is interferometry. So as I said earlier, so the interferometry techniques works based on the sensitivity to density itself. So here what you see, the dark and the bright bands, it is an interferometer pattern, or the, so in your class 11th or 12th you must have studied this double slit experiment where you have done this interferometry patterns, right? So bright and dark bands. So here the optical setup is bit more complex. So what we have is like upstream, we have again same thing. So we will do all this business to make it parallel, and we will make it to fall onto a mirror, which then falls onto the concave mirrors C1 and C2, or the spherical mirrors, whatever. So then that will become parallel. And what you do now is you use a special kind of mirrors, so which partially allow the light to pass through it and partially allow the light to deflect. So the part of the light will deflect and part of the light will pass through. This is what you exactly use in double slit experiment also. So right, so now the part of the light which is falling on passing through this mirror P3 will fall onto mirror P1, and all of those lights will be reflected. Now what you have is, say it's a test section, part of the light which is passing through, say I have a object which is sitting somewhere over here. So there is a shock wave which is coming going like this or something like that. So now what happens, the part of the light which doesn't see a shock wave and the part of the light which see a shock wave will get a different way, the like the deflection. This one will have zero deflection, this one will have some deflection, right? So because of that, so it sees a different velocity of light because of the change in density. This is a different velocity to the light. So both of them will get a different velocities now. So because of that, now you see those light which is falling onto this mirror P2, which all of them will be reflected, and there is a mirror P4, which is again the filter kind of thing. So which allows this light plus which also reflects these lights which is coming from P1. So now what happens? There is a light which is coming from this part and there is a light coming from this point. So now all of those light wavelength which are in phase will give you the bright band. All of those light rays which are in out of phase will give you the dark band. Based on that, whatever you record in the screen, you get an interferometry pattern. This is the basic idea. You guys know the double slit experiment. Similarly, uh, like in a similar fashion, this also works. But complexity is there to set up all those mirrors and this either this half silvered mirrors or the splitter mirrors and the plane mirrors in place precisely. That is where the complexity of the setup lies in. Okay. So interferometry is a very beautiful technique, but mostly people stick on to a steering technique because it's moderately easy and it also gives a much more spatial variations of the flow structure compared to shadow graph. So that is why people usually go with the steering as the main diagnostic technique, and often shadow graph is also used. But interferometry you see a rare occasion. People use it, but it's a very rare because of the complexity in this optical setup. Okay, here is one more interferometry image. You can see how this dark and these bands are there. Okay, I'm not going to give you the physics of this flow field as of now. So it's just for the illustration purpose I have kept here. Okay, so this concludes our visualization technique topic. So let us see one or two questions which is asked in previous year gate. So one question is the shadow graph flow visualization technique depends on. So can anybody give me the answer, correct answer? Option C is correct, right? It depends on the second derivative of the density with respect to spatial coordinates. Correct. We have already seen. So in the figure shows the schematic of a setup for visualization of non-uniform density field in the test section of the supersonic wind tunnel. This technique of visualization of the high-speed flow is known as. Which technique they are referring here? Or the schematic is showing? It's option C again, right? It's the shadow graph technique. So like whatever asked in previous year gate, they are relatively straightforward. After attending this class, like I'm damn sure like you guys are going to make no mistakes in flow visualization technique problems. Okay. So we covered in actually in depth compared to what you guys are aware of. Okay. Okay. So this concludes our discussion. For more information, you guys can contact us at IIT and Gate classes. If you have any question, I'm happy to take. Maybe later in the classes also can discuss. Thank you.
So Akshay, there is one person was asking to repeat this Gladstone Dell equation.
Gladstone Dell equation. Huh?
Yeah.
Okay, so as I said earlier, this is a fairly straightforward idea we have studied in our high school physics. That is like the refraction of light. So the refractive index is a function of density of the medium. That's what Gladstone law says, right? So n is equal to 1 plus beta times rho by rho s. That is what the law is, where it actually relates the refractive index to the density of the medium. I'm not going to give you the derivation part of it. It is not important. All we have to understand here is like the refractive index and the density of the medium are related. What you have studied in your high school physics is Snell's law. That related something like n is equal to some kind of sine inverse of something, right? Or sine of something. So the angle, right? So that relates to geometry of the light path, whereas this relates the density of the medium. That is why I introduced. So it's function of density to make sure like uh, we can use this property, the change in density, as in a better use. Okay, no need to worry much on that law. Other than that, like you are not going to get any question out of this law. Okay, anything else?
Any question? Those who are watching this session on IGC online platform and those who are watching on YouTube. Subham, how was the session? So you have really did a lot of hard work to set up your own setup. It was very nice to see that the whole
Yeah,
setup
yeah,
you
yeah.
made it. So guys, Akshay has done a lot of good work at ISC, and soon he will be leaving for his PhD abroad. Yeah. So any more question, guys? Surendra, Devendra, any question? So Devendra, you want to get in ISC? You can follow always Mr. Akshay. Yeah, Gokul, Matik, Monica, Pritam. Okay. So I think done, Mr. Akshay.
Yes, sir.
So guys, those who have watched today's session, we have another session tomorrow, demo session for strength of material, evening 8:30 onward. Sorry, I think I have given 8:30 time, right? Yeah, 8:30. So guys, do attend that session, and then we will start July batch from 10th of July. So that's all for 2 days. Yeah, yeah. So thank you all for joining this session, and keep putting your efforts. Thank you all. Bye.
Okay, then. See you. Yeah.
Thank you, Akshay. Bye.